Hi, welcome to Online Science Labs. I'm Trina Kilty, and I'll be your tour guide for today's web tour. A little about me, I taught online physical and historical geology for more than 10 years. When I started in the year 2000, labs were pretty primitive, and they consisted of generally a video cassette that was mailed to the student. And on the video cassette, it consisted of each lab was about a half an hour of a program of a lecturer, an actual person standing there and lecturing. Um, and then that was interspersed with a landscape, maybe, or some diagrams, shots of those, somewhat similar to an overhead transparency that you might look at in the classroom. After watching each program, the student would complete a 25 question multiple choice uh, assessment and email that to the instructor, and that was their lab. And then they would move on. So, to respond to what I considered a pretty dull, passive online laboratory experience, I designed and wrote lab manuals for physical and historical geology. And I worked with a company to develop a lab kit with all the materials that they would need to do these labs. So, the company, what they did was sent out a box to the student. It looked like this. You got it in the mail. And you ordered it like a book from the library or the books, not the library, but the bookstore or online from the company themselves. This came in the mail, and inside you got the lab manual, which started in paper form but then moved to a CD-ROM. And then you got all the materials to do the lab, such as this one is for historical geology. You got some scientific equipment to actually identify rocks and minerals. You can see there's different things in here, such as a hand lens, some dilute acid to test rocks, a penny for a scratch test. You got a bag of rocks, not a box, well, it wasn't a box of rocks. This is sedimentary rocks that you would identify that fossils are commonly found in. You got goggles, some safety equipment, and you got some fossils. You can see these are in bags, and then they have a drawing of what it is you're looking at, because a lot of these students had never really seen a fossil before all by itself, and kind of, there's a snail. You can kind of see that. And they all came in their own bags along with a little a bag of fossils so that you knew what they were. There's teeth in there, shark teeth. This is a big bag full of stuff. And then you also got some soil, gravel. This happens to be pea gravel that you did some experiments with, and some petri dishes, and cups for different experiments, and things like liquid latex that you used, because we actually made, one of our labs was to make a fossil using a leaf or something you found outside. So that's what was in the lab kits, and what the student would do here was access the appropriate lab exercise and then follow the directions and complete the lab using their materials, and then write up the results into a formal lab report. I did not do multiple choice. I had them write a lab somewhat similar to what you do in introductory geology labs on campus, and then they would submit that into a Dropbox online in the learning management system for the course. So I found these labs to be a pretty solid way for students to learn the lab component. I thought it was authentic, it was hands-on, definitely, and it could address the experiential aspects of lab. However, there are some scientific concepts that can't be taught by hands-on geology, by actually looking at something. Such as, this would be internal Earth processes. For example, you can't journey to the center of the Earth, so you can't see some of the things that are going on in the interior of the Earth. And as well as maybe some chemical processes that you can't really, they're too small to see. So for these concepts, it seems like computer simulations might do the trick. So let's take a look at some of those. Hi. So let's take a look at the fantastic FETs here. This is a website that's associated with the University of Colorado Boulder, and it's a website with free interactive science and math simulations. There's simulations for earth science, chemistry, biology, physics, math. They're also arranged by grade level, so you can look for elementary school, middle school, high school, university, which is what I've got it on right now. I used the university options, and when we looked at the options, I tried to look for things that can't be seen in person, such as I skipped over this one, the balloons and static electricity, because you can really see that. There's another one of a skate park, and that's another one that you could really see. You could do that in a face-to-face lab and or go on a field trip and actually see that occurring. So I tried to focus on things that were interesting and stuff that you could not actually see, because I thought that accomplished the objectives a little bit better. So let's go into charges and fields. Okay, in this one, I also looked for one of my requirements on this WebTour were things that were really simple and intuitive. The learning curve has got to be pretty low for these simulations, or else you risk spending all of your time explaining how to run the simulation rather than explaining the science concepts of what the simulation is trying to show you. So here we see, if we just start fooling around, we see that we can move positive and negative charges into the field, and then we can put sensors in there that will measure things like voltage and so forth. And then if we check up here, we can get layers of information, and we can add and subtract those and get more information. We can even put a grid on it, which I found was maybe a little bit too distracting, and you can keep adding them, and it is very interactive, and it's a way of looking at charges that cannot be really viewed, or they're not truly visible otherwise. And so I think this gives you a good example of that. Okay, here's another one of atomic interactions. Now in this one, you choose the interaction. So let's say I wanted to interact neon and oxygen, and then you play it to see what happens. Hopefully. There we go. Maybe not. Okay, you see the interaction, and what happens is this moves up, and then you can kind of watch it go on that graph. Let's see if that'll finally. There it goes. Okay, I just had to be patient, and you can watch it as the atoms get closer and then repel each other and move away. And again, that's another example of something that is not really visible in real life, so it makes sense to show that in a simulation. Now you ask, what could we do with all of this? How does this translate to an actual lab activity? So let me show you here. Here's something that I downloaded, and this is an activity on glaciers. This is a glacier simulation activity, and so here you see something that looks like an actual lab exercise. It has objectives. It has some pre-lab material for answering about prior knowledge. And then they show you how to go to the link to go to the simulations, the step by step, some hints like turn off the snowfall effect, play this for 5 minutes, and then answer some of these questions. So this would be an example of how this all works out in an actual lesson. Unfortunately, I'm not able to show you the glacier simulation because it's in, I think, a Java format, and I have a Mac, which leads me to discussing some of the drawbacks with simulation labs. Okay, here's a photo that you can answer some questions on. What I showed you before, the two examples, was in HTML5, which is accessible across all platforms and browsers. When I tried to access other labs, I got an error message. And what I did, I downloaded the app for the iPad. That cost 99 cents. I went ahead and bought it. But overall, I would call this a disadvantage to simulations in that as an instructor, you would have to state upfront what all of these simulations require in terms of computers. And then probably you would run into technical problems with your students at a distance. Students might get frustrated as well. I know I did. When the simulation doesn't work, it doesn't download, etc. You've got a different computer. It reminds me of the early days of teaching online, just in general. We tend to think of the days of plugins and incompatibility are over, but this is still pretty cutting edge stuff. And PhET is coming along with the HTML5. But they've still got a ways to go. A lot of those labs that I didn't show you and am not able to show you need to kind of get there with the HTML5. I personally would recommend doing these simulation labs in a face-to-face class held in a computer lab where you know everyone has the same computer, and as the instructor you have access to tech support. That controls for all these different computers. But however, this can be difficult due to scarce resources, regardless of whether you're of what grade level or teaching post-secondary. You've got to schedule time in the computer lab, make sure you've got tech support, and you've still got the learning curve of having to learn this yourself better than the students. So let's go to the second stop on the WebTour. We'll pause that. We're going to go to NetLogo. So we're going to up the ante a little bit technology-wise. Our second stop is NetLogo, and this is a free open source website affiliated with Northwestern University. With NetLogo, you can create simulations that encourage students to use hypotheses or guiding questions, variables, and results as they build models. The sample, which is over here, is from social science, and it's about how people will cluster at a party or a gathering. In this sample model, you can experiment with tolerance and male to female ratio, that variable, and they show it to you there. It's very abstract. It's not even stick figure people. Well, I guess it is sort of, but it's pretty abstract. But you can experiment with variables such as this ratio, and then you can kind of make predictions and test them to see if they come true in regards to, do males and females tend to cluster together or mix at a party, and how you might sort of affect that. So here's some more examples of these models. The first is system dynamics. Let me go to that one. There we go. And in this one, this example that I found the best that I could relate to is the interactions among wolves, sheep, and grass. That was easy for me to visualize. Scrolling down, and then they translate that into stocks, variables, flows, and links. For example, stock can represent population of sheep, the water in a lake, the number of widgets in a factory. So it sort of brings these very abstract concepts back to life. However, how it works, you can see it's a pretty simple diagram. And yes, you have to code. They have hints for coding. Here's some code tab, tutorials, they have those, and they also even have a blog style website that's available for help. But in the end, yes, you've got to code these things to make your model. Let's look at another one. Let's go to the robotics. And that's There it is. There it is. I was looking for it in the wrong spot. And here's the robotics net logo lab. This is a little more visual. You can do things with engineering design, which I know is quite popular and kind of recommended to do with, for instance, secondary science. You can include things in here. You can kind of code those in, these sensors that could gather environmental data like temperature, for example, or light or touch. And then you can program that into an output, such as a motor that you could run, or a light bulb that could turn on, or even an appliance. You could drive around a toy car using this. And I think that's down here, controlling a car. Um, and then here's some more examples of the code that they give you, and an example of a simple sensing project. Now, the final example that I'm going to show you is something that I could relate to because it has more to do with my content area. In geology, we often struggle with teaching students spatial thinking or thinking in 3 dimensions. And so here is a 3-dimensional model that you can build. So they've got some introduction, a tutorial, and a dictionary to help you through it. So you could build something like a mineral cut crystal or a cutaway of the interior of the earth to give students a better visualization of what's going on. Overall, I find this site to have a pretty steep learning curve, partly because I am not an expert coder, so I find that aspect more than a little daunting. I think in terms of cost benefit, there's a huge cost involved with this in terms of time. As the instructor, you've got to know it better than the students, and that involves a pretty big time investment if you start like I do basically from scratch. The returns might be pretty good in terms of showing students something that they can't visually see, such as a crystal form or the interior of the earth. However, pragmatically speaking, if I was an earth science teacher or even a college instructor and I came across this site, I would honestly feel too pressed for time to really dig into it and to come up with a model and to create one. And I think that it could be a large part of the reason why simulations have not quite caught on and are not quite mainstream in labs in general, and especially as the online component of a lab. Now, let's go to the third site. Here's an example of a remote lab. Well, not exactly, but let me get you pretty close to one. This is the MIT Remote Lab website, and to get into this, I had to register, I had to wait to be accepted by them, and then I had to apply to get into this group. Once I did all of that, I gained access to these example labs. However, when I tried to go in and have a look, for example, the voltage one, I got an error message. You also have to log in. It times you out really quickly. Okay, I got an error message. I, again, do not have a compatible computer. It looks like there's some issues with Chrome users and Windows users, and Java just doesn't seem to work at all on a Mac. So again, I'm running into some technical problems and some computer problems that in a face-to-face lab where you've got control over the computers and can work with tech support, this might work. But if you've got an online class in the first place that are also trying to do online labs, you've got layer upon layer of possible technical difficulties here. So let's go into the remote lab as far as we can go. Here you see some computer requirements. So what you've got to do is please download and install this LabVIEW 2011 plugin. You must run the experiment. You need to schedule it and then redeem your session at the remote lab. So, as you might imagine, they can't have just people going in there and doing it one on top of the other. So you've got to schedule your time, and then you've got to go in and redeem your session and actually run that experiment. So all of this sounds feasible in theory, but again, I find that the potential for frustration is really high with students especially if they're already at a distance, especially if this lab is online in the first place. If the instructor just places, for example, the website in the learning management system, think about all the layers that I had to go through in order to get to this lab. And I'm not done yet. I haven't downloaded this plugin. I don't have the right, I have a Mac for one thing, so I can't go any further. I would now have to go find a Windows lab. So I would probably end up, let's just be honest, going into some campus, and trying to get on a different computer that has access to this, only to then schedule my remote lab at yet a different place and a different computer, and then redeem that session, run the experiment, and then write it all up. Uh, it's a possibility. There might be some really good benefits here in terms of running voltage experiments, for example, that you might not be able to do otherwise, especially if you're working with students who are online and they're doing this online for a reason. Um, but the cost is pretty high. The instructor has got to become an expert in this. And then the students who've got to navigate through all these various downloads, plugins, and compatibility issues also wind up learning a lot about technology and their way around a computer, only to get to then a voltage lab, which is not, that's another whole level of all the content area that they've got to learn. So I hope you've learned something from the web tour. And please answer the question prompt in the module in the design lab about this web tour and discuss your impressions about it. And that's about it. Thanks for watching.